What's going on, players? Augustine Amaro here, Ace Tutoring. Let's get started.
3, 2.
Now we're talking about Grignard reagents, and they're really useful for making new carbon-to-carbon bonds. The first part of this is the Grignard synthesis. And so you don't have to know the mechanism for this. Normally it's not tested upon. Just take my word for it. And if not, that sucks, because I'm not going to go over it. But what you do want to know is this transformation occurs via a reduction reaction. And I guess to kind of get a little bit into the theory, it's a reduction because the carbon is going to gain electrons, which hopefully you remember, the Leo Gur from Gen Chem. And so this is useful for giving this carbon a negative character, a nucleophilic character. And so all that you want to know is anytime you see this magnesium and ether and a halogen, and this could be any halogen other than fluorine. And then it also turns out that the bigger the halogen, the more readily that you will form the Grignard reagent. So iodine would work better than bromine, would work better than chlorine. And so the other thing you want to know about this is you need to use an aprotic solvent. Why? Because Grignard reagents are really sensitive to protic solvents. In other words, this carbon is going to end up being carbanion. And so if you have a protic solvent, then that carbon will just take a hydrogen via acid-base reaction, and it defeats the whole purpose of having a Grignard reagent, which again allows you to create new carbon-to-carbon bonds. So that's about as much as I want to get into the theory. Let's take a look at some examples. Okay, so essentially what we have here is the Grignard reagent acting as a carbanion, which means it's going to act as a nucleophile. So the organometallic of the magnesium bromide to carbon complex really should be redrawn every time you see that carbon bonded to that MgBr or MgCl or MgI, whatever the case may be. Just redraw the molecule so that you give that carbon bonded to that magnesium halide a negative charge. And so that's what's useful about the Grignard reagent, because normally we already know, hopefully at this point, if you passed Organic Chemistry 1, carbon does not like to have any type of charge, negative or positive, especially negative. So the Grignard reagent is the organometallic complex that allows you to give carbon a nucleophilic character. Now, you want to be familiar with some of the limitations of that reagent. But for now, this is also a great example to review the nucleophilic addition of the carbonyl carbon, which is a fundamental reaction and mechanism that you have to be familiar with. And so if you notice, what we have here is a negative charge, a nucleophile attacking this carbonyl carbon. Move the pi bond up as an electron pair to that oxygen, giving that oxygen a negative charge. So usually the step after this, because remember, you don't want to end up with a negative or a positive anywhere as a final product. So if you ever notice a step that says workup or quench, it's the same thing as if I were to write H3O plus. And so ultimately what I end up making is an alcohol. This oxygen comes to pick up one of those hydrogens, and this ends up turning into OH. Now, one thing to keep in mind, if instead of using H3O+, I would have used D3O+, or D2O, keep in mind that deuterium is just an isotope of hydrogen. And so all that means is, suppose I had D2O before, all you would do is make that OD instead of OH. Very important that you pay attention to what the final step of the workup is. And sometimes you end up having this oxygen attack another carbon molecule via SN2 type reaction. But we'll take a look at some of those later. And so if you notice, instead of drawing this whole benzene out again, I just put it as pH. And again, you should know when the ring, the benzene, is directly attached to the longest chain, then we're going to refer to it as a phenyl group. If there's a CH2 between the longest chain and the ring, we're going to refer to it as the benzyl group. So make sure that you know that. And so first thing when we're doing nomenclature is figuring out which of these takes priority. And of course, the alcohol does here. So we're going to find the longest chain, so we give the alcohol the lowest number possible. So would you start down here or up here? Well, being that you want alcohol to have the lowest number possible, you go 1, 2, 3, 4. So this has to be a butan 2-ol. And then always work backwards when you're doing nomenclature. And then all you have to do is fill in the rest by putting the substituents in alphabetical order. And so that means you're going to put 3-methyl, 2-phenyl, butan 2-ol. If something is optically active, as a recap, we learned way back in Orgo 1, that means that it has to be chiral. And so if you notice, when we attacked the ketone, and again, I'm just drawing the ring as a pH here, because the attack takes place at this carbon, we can refer to this carbon as a pro-chiral center. In other words, saying the moment you add another substituent to that, then this carbon is going to become a tetrahedral, sp3 hybridized, and because it's connected to 4 different substituents, then that means that that will be a chiral center. And so this also highlights part of the mechanism of the nucleophilic addition to the carbonyl group. And so similar to SN1, when you attack an sp2 carbon, you can attack from front or from the back, or top or bottom, however you learn. It should make sense then that this would form a racemic mixture. And because we form a racemic mixture, when we attacked over at this carbon, we formed 1 chiral center, which means you could have had both R and S forms of the molecule. And again, because here's my molecule kit for you. So similar to SN1, anytime that you attack at an sp2 hybridized carbon that is trigonal planar, it looks like this, right? It's all flat. Then the nucleophile, which will be, I guess, this marker in the green, can attack from the top or from the bottom. So if I'm looking at this sideways, it could have attacked from the front, giving you that wedged group here, versus attacking from the back, where it gives you that one. So the product obtained will not show optical activity because these two cancel each other out. How many H1 NMR signals would you expect for the product obtained? So here, I would want to redraw the benzene. And the first thing you want to do when you're doing HNMR, you want to look for symmetry in the molecule. Is there symmetry in this molecule? Absolutely not. And so then that means that I'm going to treat each of these hydrogens as a different magnetic environment. And so don't forget that you would also get a reading for this hydrogen. Now I'm going to use letters for the designation of different hydrogen environments. That's just how we did it here. We normally tend to put letters for hydrogen environments and then numbers for carbon environments. So I have A, B. Now this B represents these 3 hydrogens for that methyl group. And even though I have 2 more methyl groups, they're not going to be the same. Now these 2 would be the same because of free rotation. And if that doesn't make sense, watch the video on HNMR. And here we see that you have this hydrogen is the same as this one. And because these hydrogens are further away from that electron withdrawing group, then these would be different than these hydrogens. And of course, this one hydrogen of the benzene, there is no other one like it, so it also gets its own separate signal. And so one thing to look out for, oh wait, and I forgot one more, right here. We get this hydrogen. So here I have a total of 7 hydrogen signals. If all this labeling gets you confused, again, please refer back to the HNMR video. But I will tell you, if you ever see a HNMR with peaks, some type of peaks, crazy peaks going on between 6 and 8, you probably have the presence of an aromatic, because those are really deshielded. And the other thing that I would look out for in this type of HNMR is the presence of that one single peak between maybe 4 to 5, maybe even 6. Somewhere around here, you'll notice a singlet referring to this hydrogen of that oxygen. Okay, so another follow-up question you could do here is, what relative change would you be looking out for in the infrared spectra when you compare the starting material versus the end product? So it should be pretty obvious by now. Here you have that obvious sharp carbonyl peak. That'll be somewhere around, say, 1700, 1735, maybe. And again, that's going to correspond to that carbonyl stretch. And again, here we're just comparing the IR of starting product to the end product. And here your obvious change is going to be that at around 3200 to 3600, and that's that OH stretch. That would be the one big thing you're looking for, right? Normal level. And so keep in mind too, this actually be a lot more narrow, because the more substituted the alcohol is, the more narrow that broad stretch is going to be. So I hope this makes sense. Hope it helps. Let me know your feedback. See you next time.